this video, we are going to talk about cardiac rate, the contractility of cardiac muscle. We're going to talk about stroke volume and explain the Frank-Starling law. In the upcoming videos, we'll talk more about venous return. So some terms that you should know. Cardiac output is the volume of blood pumped per minute by each ventricle. The volume of blood pumped per minute by each ventricle. The stroke volume is the amount of blood pumped per beat by each ventricle. The amount of blood pumped per beat by each ventricle. And this comes out to be about 70 to 80 milliliters per beat by each ventricle. Heart rate, on average for an average person, it can range anywhere from like 50 to 90. So on average, it's about 70 beats per minute. So if we multiply the stroke volume, which is about 70 to 80 mils per beat, times heart rate, 70 beats per minute, we would get the cardiac output, and that comes out to be about 5,500 mils per minute. If you can remember, we spoke about, the average volume of blood in an individual, and that's about 5 to 6 liters. And so what this means is that, if we take the average of that, let's say it's 5,500 milliliters or 55.5 liters, same thing, right? 55. That means that your heart pumps about the whole your whole volume of blood in 1 minute. Your heart pumps all your blood within 1 minute. Another way to think about this is that one drop of blood, for it to go from the right atrium through the pulmonary circuit, through the systemic circuit, back to the right atrium again, would take about 1 minute. So that's another way to think of it. So we're going to talk today about what can impact our cardiac output by impacting our cardiac rate or impacting our stroke volume. So we're going to talk about, and these arrows are a little displaced, sorry. We're going to talk about how our cardiac output can change because of these variables here, cardiac rate and stroke volume. And remember, stroke volume is the amount of blood pumped per beat by each ventricle. And so, maybe you've experienced this on your own. We logically know that our heart rate increases with activation of the sympathetic division. The sympathetic division releases epinephrine or norepinephrine, and that will produce cyclic ANP. And remember, those cyclic ANP are going to impact those HCN channels, and those are going to increase the rate of the heart rate, increase the rate of depolarization, increase the rate of these pacemaker potentials, as we can see in like this steeper curve here. This is called a positive chronotropic effect. Positive chronotropic effect, that just means, chronotropic means like impacting time. And so positive chronotropic means increasing the rate. And, logically, we know that our parasympathetic division is going to decrease our heart rate. It does this by releasing acetylcholine. Acetylcholine opens potassium channels, and it causes for leakage of potassium out of the cell, and that is going to reduce depolarization. And so we see a slowing of our cardiac muscle pacemaker potentials here. This is called a negative chronotropic effect. It's going to reduce the rate, decrease the rate, and decrease the rate of the pacemaker action potentials. So if we were to look at where the sympathetic and parasympathetic activate, they both are activating the SA node. They both are activating here, and so they're going to have their effect on the SA node. And this is what allows them to either increase or decrease the cardiac rate, increase or decrease the heart rate. By increasing or decreasing the pacemaker potentials or the depolarization in the SA node. And then notice that everywhere else, the sympathetic nervous system is mapped out here, has innervation here. But in the parasympathetic, it does not. And so the sympathetic nervous system is able to increase contraction, and I'm talking about the muscle here, sorry. Increase contraction of the muscle because it innervates the muscle walls, whereas the parasympathetic cannot. And so the parasympathetic can decrease cardiac rate only by decreasing the rate of the SA node, the depolarization there, or by decreasing the depolarization at the AV node. So remember that the stroke volume is the amount of blood pumped per beat by each ventricle. And it is related to or determined by 3 different variables, which we're going to talk in detail now. First off, we have our end diastolic volume, and we spoke about this in the last video. End diastolic volume is the volume of blood in the ventricles at the end of diastole. Diastole is relaxation, and at the end of diastole means right at the end of relaxation, so while they're filling, right before contraction. So end diastolic volume is the volume of blood in ventricles right before they are about to contract. This is also called preload because it's like preloading the ventricles with, what they're about to pump out. And what we find is that our stroke volume, the amount of blood that the ventricle beats per minute, is directly related to stroke volume. And that makes sense, like the stroke volume is obviously going to matter how much blood is in the ventricles to begin with before contraction. And so they're directly related to each other. There is another variable called total peripheral resistance, and that is the frictional resistance to blood flow in the arteries. And what that means is, say you have your heart, and then you have an artery pushing out of it, and there is a lot of resistance here because there's a lot of blood pressure, there's a lot of blood in here. That's going to push back on the heart. It's going to push back on the blood here. And so when this is high, the stroke volume is going to be lower. If it's super high, it's going to be lower. If it's lower, this will increase the stroke volume. And so what we say is that it is inversely related to stroke volume. When total peripheral resistance is high, stroke volume is low. When total peripheral resistance is low, stroke volume is high. And this is going to matter when, you think about patients with high blood pressure and what that means on the load on the heart. This is also called the afterload. So that's the second variable. And then the third variable is the strength of contraction, the contractility of the ventricles, how strong our myocardium is able to contract our ventricles. And we're going to talk about 2 ways in which they are controlled. Intrinsic control, intrinsically, and intrinsic means inside, so by their own cells. And this is done by the stretch of the cardiac muscle itself, or extrinsic control. So extrinsic means outside, and notice that it says sympathoadrenal system. So this has to do with the sympathetic nervous system and the adrenal gland. Okay, so there are two researchers back in the day named Otto Frank and Ernest Starling, and they researched the heart, particularly the heart muscle, myocardium. And what they saw is that when there was an increase in end diastolic volume, it increased the contractility, and then thus increased the stroke volume. So they saw this connection, this correlation between end diastolic volume and contractility and stroke volume. And so, this graph is showing when end diastolic volume would increase, stroke volume would increase too. Because there was a greater contraction in the heart. The muscle fibers of the heart, the cardiac muscle fibers, would contract more strongly. And so what they saw was that there was this intrinsic control of contraction. And by the way, in that last slide where it showed, this correlation between EDV and stroke volume and contractility, this was independent of the nervous system. It's like they took a heart and kept it going with pumping blood from a bottle, I don't know, and this heart would increase its contractility whenever there was more blood left over at the end of diastole. And so this was independent of any nervous system control. They found that this was intrinsic. This came from the myocardium itself. And what we've learned is that it is due to the stretch of the myocardial cells. And so what they saw was that increased end diastolic volume, the more volume you have at the end of diastole, stretches the myocardium. The more you have, it's going to stretch it out more, right? And so what that did, or what they saw it did, is that it increased contraction strength. And so you can see in these pictures here, when there was, let's start at A, when there was low volume at the end of diastole, notice that the myosin and actin, they overlap each other a lot. There's not going to be enough space for contractile strength. And we see that here. There's not a lot of contractile strength. You can see the tension. As it stretches out even more because of more volume in the ventricles at the end of diastole, it would be able to contract stronger because these myosin can attach to more actin filament. As it stretches out even more, again, it's just going to increase the strength because these myosin can connect or attach to more actin. And then even more, as there is more stretching, there's going to be more space for pulling of those cross bridges. And so that increases the strength of our myocardium. I want to remind you about skeletal muscle. Skeletal muscle, we learned about the length tension relationship there, and this is not true. This is not true of skeletal muscle. Skeletal muscle, remember, there was like a sweet spot. You don't want it to be too close together because, again, just like this, it's not going to be able to contract very far because, the sarcomeres are already short. You don't want them to be too far away either because then the myosin won't be able to attach to actin. So there was kind of a sweet spot for skeletal muscle. That is not true of myocardium. The greater the volume at the end of diastole, the greater the the strength of the contraction. So this is describing the intrinsic control, because remember that Frank and Starling, they did this independent of the nervous system. And so that is how they found that this was because of the myocardial cells themselves. But there is also extrinsic control of contraction. And so extrinsic control can be due to our sympathetic and parasympathetic divisions of our autonomic nervous system. With the sympathetic division, it will release norepinephrine or epinephrine from the adrenal gland. And what this does is it's going to increase the strength of contraction, The way that does this is by increasing the calcium concentrations that are available to sarcomeres, increasing that intracellular calcium. So this is called a positive inotropic effect. It's going to increase that contractility via increased calcium concentration. The parasympathetic releases acetylcholine, and acetylcholine doesn't have a significant effect on contractility. So it actually does not increase or decrease the strength of contraction. So I want to remind you of this table that we spoke about before. The sympathetic nerves are located in all these areas of the heart, not only these SA node and AV node, but within the muscle walls. And so they increase the contraction strength. Notice that the parasympathetic divisions are not located within the muscle walls of our heart, and so they do not impact cardiac contraction strength. So back to this image here, remember we spoke about cardiac rate and how the sympathetic nervous system can increase this, which is called a positive conotropic effect. And the parasympathetic can decrease this, which is called a negative conotropic effect. Chrono has to do with time. And so this would increase the rate, decrease the rate. And notice that the parasympathetic nerves does not impact the stroke volume. It does not impact the strength of contraction, and so it does not impact stroke volume. So I'm going to write a big X here. The sympathetic nerves does, because of that norepinephrine or epinephrine release that can increase the strength of contraction. We find sympathetic nerves within our muscular walls, and that is going to impact stroke volume. And then we have the intrinsic control of Frank-Starling, and when we have increased stretch from increased diastolic volume, that will in turn increase our stroke volume.